Testing on YouTube. Testing on YouTube. All right, we're live. How's it going, Tawfiq DP? We got Abraham Lincoln dropping thoughts on the stream before it even starts. How's it going, Josh Phillips? All right, and then we should be set for X as well. Excited for this one. Yeah, me too. It was actually pretty good. I was reviewing the papers this morning, and you know, it's pretty cool set of results, and I think they all kind of nicely line up, and they all kind of point in a direction that is quite promising for the AGI race. All right, I think this is probably going to start soon. All right, I think we're live on X as well. Let's double check. Make sure the volume is working. Something's wrong. Let me try X again. Test on X, test. Test. All right, I think it's working. Let's get this started. So, let's blow this horn and then we'll get started. All right, welcome to another Hoopo stream. Today we're going to be reviewing a couple different papers that have to do with these ideas of self-play and synthetic data generation and situations where you can kind of heuristically generate data sets. And the name of the stream is called AlphaGeometry and FunSearch. Those were the original two papers I wanted to read, but then I added a couple more papers which I think are relevant. So the four papers that we will be reviewing today are this first one here. This is called Solving Olympiad Geometry Without Human Demonstrations. This is a paper published out of DeepMind, Google DeepMind here. And this is a little bit older, right? They received it 30th of April 2023, and it was published the 17th of January, so just a couple of days ago. And that actually just shows you how slow Nature is. Nature is the journal in which this is published. It's one of the most prestigious journals, but because of that, they have a very slow process of kind of approval and eventually publishing. The second paper we will be looking at today is called Mathematical Discoveries from Program Search with Large Language Models. This was also went into Nature, so also a very slow process, and even though it was received, or at least written in 12th August 2023, it didn't come out until 14th December 2023. This is also a DeepMind paper, although this is the Google DeepMind in the London, UK office rather than this one here, which is the Mountain View, CA office. Okay, so those are the two DeepMind papers, which I actually think are the two weaker papers that we'll be reading today. There's a couple problems that I have with these, and the two good papers that are related that we're going to be reading today are this one here. This one's called Code Generation with AlphaCodium from Prompt Engineering to Flow Engineering. This is from Codium AI, which is some kind of startup that was spun out of this particular work. You can see how all the authors have at Codium AI emails. They probably just created this startup because of the good results in this paper. This one came out 16th January 2024, and I think this one is the best. I really like the way it's written. I think the results are strong, and it even got a call out from Karpathy on his Twitter, so we'll look at that once we get there. The final paper that we will be looking at is called Self-Rewarding Language Models. This is from Meta and was released on the 18th of January 2024, so also fresher. And this one is pretty good, but it has, I think, a couple points that are worth kind of thinking twice about. but it's promising in terms of what it means for AGI. How's it going, Ed? Good morning. Is this AGI, and will humanity be doomed? This is not AGI. I think AGI was already achieved with the original GPT, right? The G in the word AGI stands for general, and I think the general nature of language models, that's fulfills that definition to me. So I think we've already achieved AGI, and what we're really trying to achieve is something called ASI, artificial superintelligence, which is not just a general type of intelligence, but a general type of intelligence that is superior in pretty much every single thing, right? And we're very close to it, and I think these type of ideas here, such as in the self-rewarding language model and some of this, what is being known as flow engineering here with this code model, and then some of these more kind of brute forcey kind of solver stuff, I think that is the path to artificial superintelligence, in the same way that the way we surpassed human level performance in Go and chess was done through this kind of like iterative kind of creating your own data to train on and then improving through self-play, right? That there's a reason that's the way that we got to superhuman performance in Go and chess, and I think we're going to get to basically superhuman performance in kind of reasoning and coding, and then eventually that superhuman performance in reasoning and coding will start to transfer to a bunch of other tasks, right? And then once it starts transferring to all the other tasks, then it's kind of, I want to say game over, but game over has kind of a connotation of like that's the end of humanity, and I think it's really not. I think we can kind of all look forward to a future where we all just kind of get to play VR games, and there's robots that serve us and cook all our food. So I think it's going to be pretty good. Jay hitting us with the horn of Abraxas. That's quite the reference there. Abraxas is a deity, an ancient kind of like two-faced deity. I think the publishing process is slow, so academics can get away with doing nothing but wait for acceptance rejection from, that's another comment from Jay. Yeah, that's why I prefer kind of the archive style publishing model, where you basically just throw this up on archive and people read it within days of it being put up, rather than this kind of nature old school style publishing where you put the work and then it's like a year before anybody actually looks at it, and then you don't get to talk to the authors until you actually go to the conference, which is even longer than that. I think that's kind of the old school work cadence, but nowadays with the kind of hyper accelerated internet world, these type of papers are more so kind of new school, right? Where they just release and then next day you're already kind of reviewing them on the internet. Okay, so let me take a little sip of this here espresso. Pro tip, when you're doing espresso, you want organic, single origin, light roast, whole bean. Those are the key words, right? You want light roast over dark roast because light roast is generally the higher quality bean. Whenever they have lower quality beans, they will dark roast it to get rid of the bad flavors. You want single origin because it means you're not getting a blend, right? Generally, when you get blends, that means that they kind of mix a bunch of other coffees. It changes over time. They're kind of buying more wholesale, so a little bit lower quality. And then you want organic just because you don't want coffees that are grown with a bunch of glyphosate. But that's my coffee preferences. So enough stalling. I think we got a nice little crowd here, so let's get started. All right, so this is the first paper. This is the DeepMind paper, Solving Olympiad Geometry Without Human Demonstration. So what do they mean by Olympiad geometry? So they're going to be proposing a algorithm called AlphaGeometry, a model. Really, it's a combination of a model and then a heuristic kind of brute force searcher that proves theorems for Euclidean plane geometry, right? So this kind of theorem proving is a type of problem. You can almost think of it like a leak code, but a kind of like a more advanced leak code and very mathy leak code that is part of mathematical competitions such as the International Math Olympiad, so IMO. IMO, and this is kind of Google image search for IMO. You can see it's basically an international competition for people that, I think it's pre-collegiate, so you're not allowed to basically do this once you're in college, but it's basically people in high school, that kind of age, maybe like somewhere like 15, 16, 17, 18, that kind of age group, they kind of compete in these national groups, and then they try to basically solve extremely hard kind of math-flavored LeetCode problems, right? So you can see all these people pretty much every single time you look at these. It's like the nerdiest people you could ever think, but pretty much every single one of these kids could probably slaughter you in any math or coding competition. So even if you make fun of them for looking nerdy, they're probably pretty well off. So that's what International Math Olympiad is. What is Euclidean plane geometry? So Euclidean plane geometry, and this is the Wikipedia page for Euclidean geometry, comes from this Greek guy called Euclid. And you can see here this nice picture of some, I don't think this was painted in the Greek time. This is probably a Renaissance painting, so there's some creative liberties here. But you can see this Euclid guy right here, and he's got a little protractor, and he's kind of like showing people some Euclidean geometry here on a 2D board with a bunch of other people sitting around kind of arguing about things. So Euclid created this whole system of geometry based around these postulates. So I think if we scroll down, here you go. So these are the Euclidean postulates. So draw a straight line from any point to any point, right? So he says, okay, you have some points. You can draw a straight line between those. You can describe a circle given a point and a radius. All right angles are equal to another, right? So, and then there's this fifth postulate is a little bit more complicated, but if a straight line falling on two straight lines with the interior angles, then two straight lines produced indefinitely meet on that. And so like kind of like parallel lines. So I'm kind of glossing over here, but what a Euclidean geometry proof exercise is basically coming up with a series of these kind of, I think they call them deductions, in order to eventually prove something. So let's find something, a little bit of an easier one here. I think this might be an easier one. So here is the problem statement. So you have some triangle with points A, B, and C. Let A, B, and C be any triangle with AB equals AC. And here what they're saying is the length of AB is the same as AC. So that's all you know, right? But you don't know these angles, right? So you don't know what any of these angles are. And the idea is prove that ABC is equal to BCA, right? I think that refers to the angle. So in order to do that, you're going to have to basically create these postulates or these deductions, and then layer the deductions in such a way that basically someone can go through and say, yep, this makes sense, 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 this makes sense. And if you have enough of those kind of collective pieces of evidence that all kind of follow one another, eventually you get to the point that you want, which is, hey, this final thing that you want proven, right? So for example, this is the International Math Olympiad 2015 P3. So P3 I think means like third place proof of this. So if ABC is an acute triangle, let O be its circumference. So you can see they've added this circle O. Okay, now that we've added their circle O, we're going to create this orthocenter of O, and then that orthocenter of O is going to have some relationship to this, which is then going to have some perpendicular angle to that, and then we're going to make a different circle and show that the center point of this corresponds to the center point of that, like kind of things like that, right? So that's what a Euclidean geometry proof is. It's basically a bunch of these kind of statements that you can verify heuristically with a hard-coded kind of what they call a symbol deduction engine. So you can it's kind of like a programming language, right? And that's extremely critical for this, right? This entire model, AlphaGeometry, really a combination of a model and this kind of brute force search. The only reason it can work is because you can basically verify the syntax of a proof and all the deductions that lead to that, right? So a computer that is not using any form of deep learning or AI can basically verify the set of these, or the list of these kind of points and things that you kind of say, these constructions, I guess. Sorry, I was calling them deductions. I think they're called constructions. So you construct a bunch of statements, and then at the very end, those constructions lead to the final solution. But those can be verified basically by a computer. And that's the whole point, right? And another way to think about this is that it's very similar to a game like chess and Go, right? A game like chess and Go has this final kind of reward function that is the environment itself telling you person A won the game and person B won the game, right? So all of the reinforcement learning that makes Go and chess AIs eventually reach superhuman intelligence is because they're basically farming information from this environment signal that is the reward. And the reward is really coming from the fact that in a game like chess and Go, you have this final thing that is telling you this person won, this person lost. The same way here is you're going to be using the fact that you can verify that the proof works, right? That the computer can go and say, yep, this is a valid proof, or no, this is an invalid proof. Okay, so let's see. I have a couple different things highlighted here. We propose AlphaGeometry, a theorem prover for Euclidean plane geometry. AlphaGeometry is a neurosymbolic system. Here, this is a combination. If you've ever heard of someone called Gary Marcus, this guy's kind of notorious for being a zealot of what's known as symbolic AI, or this was kind of an older type of AI system. You can basically think of it like it's just this giant tangle of if-else statements that has intelligent behavior from the outside, if you kind of treat it like a black box. And back in, I think it was the 80s and 90s, people actually created these very complicated symbolic AI systems, and they thought that was the future, but eventually those systems ended up getting beat by kind of deep learning type systems that learn specific structures. And there's a whole squad of those people that are still very sour that the symbolic AI isn't the way that we do AI now, so they try to combine it, and this is the hybridization of those two schools of thought, neurosymbolic systems. Hopefully I didn't piss off any Gary Marcus Andes in the chat, but all right. On the test set, it solves 25 of the 30 Olympiad level problems, and it basically is the equivalent of a gold medalist in the IMO. AlphaGeometry produces human-readable proofs, solves all geometry problems under human expert evaluation, and discovers a generalized version of the translated IMO theorem in 2004. So this makes it seem like, wow, it's pretty good. It discovers everything, but it really does not. You know, it's really kind of way more brute forcey than you think it does, than you think it is. So let's see, an alternative method for theorem proving using synthetic data, thus sidestepping the need for translating human-provided proof examples. So what they're saying here is that this system is not going to be trained with a giant data set of human-provided proofs, right? So it's not like they had 10 million Euclidean plane geometry proofs and they just fine-tuned an LLM on that, and then the LLM just spits out full proofs, right? This is a more of almost like a brute force approach that is creating its own synthetic data, and then it's training on that synthetic data. And then once it trains on that synthetic data, it can generate individual parts of the proof, right? So it generates these constructions, but then you actually run the symbolic deduction engine, which is basically like kind of like a hard-coded like syntax checker, if you want to think of it that way, that then says, okay, is these four statements that the AlphaGeometry model produced or generated, the LLM actually generated, are those valid? And if they're invalid, then it goes back and tries more. So it's kind of like this try, validate, 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 and eventually it builds a proof. But the proof that it builds is not very good. So let's see. They have an example of this here. All right, so here, this is an example buried in the appendix section here. This is figure 4, side-by-side comparison of human proof and AlphaGeometry proof for IMO. I think, actually, this is the one I want to show you. So this is the same thing, right? This is basically a problem. Let AH, BH, and CH be the altitudes for a triangle. The inner circle W touches these things. Consider the symmetric lines, blah, blah, blah. Prove that these images form a triangle whose vertices lie on W. Okay. So basically, we have to prove that certain points fall in a circle W. So here on the left, you have the human proof, right? So this is some human, some guy, some kid here at the IMO created this proof. And then here you have the proof that came out of AlphaGeometry. So the way that the human proved this is they started like this. We use complex numbers with W, the unit circle. So immediately they introduced this notion of let's change the basis of this space to account for change the kind of coordinate frame to use imaginary numbers. So the human solution is very short. And as they put it here, the human solution uses complex numbers. With a well-chosen coordinate system, the problem is greatly simplified and a solution follows naturally through algebraic manipulation. So the human solution to this is they found what they call coordinate bashing, right? They've said, okay, wait a second. If we reframe this with complex numbers, this now becomes much simpler. And because it becomes much simpler, we can now solve it in basically what this is, like half a page, not even, right? So that's kind of a very beautiful human solution where you have an original piece of insight that's very orthogonal, and then that insight allows you to basically then solve this quite easily. On the right here, you have the AlphaGeometry proof. The AlphaGeometry proof is incredibly complicated. So it has over 110 steps, right? And all the 10 steps are basically creating these incredibly complicated. It's like, okay, well, let's create another circle that bisects this thing, and then we're going to take the center point of that circle and have another triangle which intersects with that circle and that triangle, and because this circle's here, that means that this is parallel to this, and like, I'm just kind of saying nonsense there, but that's the type of stuff that this AlphaGeometry proof solver is doing. So the AlphaGeometry proof solver has many low-level steps that are extremely tedious to a human reader. So it finally gets to the solution, which is a valid proof for this particular statement, but the way that it gets to it is basically by creating hundreds of these constructions, right? And then all of them are valid, but it's basically completely not understandable. And to me, it's not really a good solution, right? So it's like you're basically solving this in a very brute force way, right? And I think this example here, which is kind of buried in the appendix section, shows you maybe, I think the biggest negative of this paper, that it's not, despite what they're saying here, where they're like, oh, look at this, it solves 25 of the 30 problems, which means it's at a gold medalist level. It's not solving them in a true kind of like human way where it's coming up with interesting kind of ideas and intuitions and then solving it that way. It's basically just kind of brute force solving these proofs by layering these constructions that are all relatively simple. Good morning, Hupo from Majetti. How's it going? No problem, man. We're just getting started. So, as we were saying, the symbolic deduction engine, which verifies proofs, this is like kind of like hard-coded heuristic, just piece of code. The engine exhaustively deduces new statements from the theorem premises until the theorem is proven or new statements are exhausted. Because the symbolic engine fails to find a proof, the language model constructs one auxiliary point, growing the proof state before the symbolic engine retries. The loop continues until a solution is found. So that's why I think this paper is weak. It's just very brute forcey. It's just basically brute forcing these Euclidean geometry proofs by layering hundreds of these constructions until you finally get to a point where you can say, okay, well, because this circle and this triangle overlap in this particular way and it bisects this, then blah, blah, blah. Right? But it's extremely unsatisfying. So how does it even... how do you even generate these constructions, right? So if you just ask an LLM to just generate constructions as is, it's probably not going to be generating constructions at the quality of this one, right? So at least this is a very kind of a brute force search, but at least the language model that is deciding what to search and what constructions to add, at least it's been fine-tuned such that those constructions are at least a little bit high quality. So how are we going to get a language model that generates kind of higher quality constructions? And the way that they do this is using synthetic data. So they create over 100 million synthetic theorems with more than 200 proof steps, which again is fucking crazy, right? Like no human would do that. As they put it in their example, this is many low-level steps that are extremely tedious to a human reader, right? So very brute forcey. But what exactly is it doing? So let's say this. This is how the synthetic data is generated. We first sample a large set of random theorem premises. Okay, so they basically create random problems. And you can do this because Euclidean geometry is pretty formally defined, and you can basically heuristically create a function which generates these theorems. Okay, we then use the symbolic deduction engine to obtain a deduction closure, which this is like the final point you want to get to. This returns a directed acyclic graph of statements. So a directed acyclic graph is basically nodes with these edges like this. The acyclic refers that there's no loop. So a cyclic graph would be, for example, if you had an arrow that goes here, then you had an arrow that goes here, and then this one has an arrow that goes back, right? So if you had a cycle, like a circle, a loop within your graph, that would be a cyclic graph. So an acyclic graph is one that does not have any loop like that. And then you can see here, look at these statements. So these are all little statements. Okay, so we're going to create EC is perpendicular to EA. So EC is this line and it's perpendicular to EA. Okay, now that you've added that, then now you can say, okay, well, HA is perpendicular to BC, and so on, right? That's how these little deductions get created. And you create this graph of deductions, right? So you're basically generating a bunch of these statements, and then you have your symbolic engine going through and then saying, this one's invalid, this one's invalid, this one's invalid. But eventually, you're going to get through this kind of a brute force way to a final construction that eventually the symbolic solver says, actually, with this final piece here, you've now created a full graph that actually is a proof, right? So now here, you can see here, this one, these are incorrect solutions, and then here you can see that this one is a correct solution. So incorrect solution, but this one is correct. So once you get to that correct solution, then trace back, which is basically saying, okay, well, now go back and basically look at the minimal dependency, right? So look at, okay, well, in order to get to this point, we needed this one. In order to get this one, we need these ones. In order to get these ones, we need these ones. And then basically prune the entire graph until you have the minimal premise, which is the minimal subgraph that eventually leads to this final deduction, or basically the final point of the proof, right? And that is a synthetic proof. So now you've basically created a synthetic proof that leads to the answer, or the proof that leads to the answer given some synthetic theorem. And that's it. That's basically it. So they run that. They generate 100 million synthetic theorems like that. But because they're kind of generating them by doing this kind of brute force search, the synthetic theorems are very weird, right? They're basically hundreds of proof steps. But, okay, what do they do after that? They basically then fine-tune a language model on that. So I think they mentioned the exact language model that they use. Let's see. Is it here? No, I think it might be. I'm trying to find my notes here. But they mentioned they start from, I don't know. I'm not going to find it. But they start from one of the Palm models, I'm pretty sure. It's written somewhere here. But they fine-tune this Palm model on this synthetic data set of proofs, of synthetic proofs. And then that fine-tuned language model that generates basically these deductions, I guess, that is used to create deductions to then solve the actual problems, right? So it's basically just recreating the same way that you created that synthetic data. You're now going to basically try to solve these actual proofs. So that's basically this paper. You know, it's not that great. You're basically just brute forcing a solutions to a Euclidean geometry proofs, but the only reason you can do that is because you have this basically fact checker. You have this symbolic deduction engine that can verify that all of these work. Right? So you're relying on that symbolic deduction engine to basically give you that feedback and be able to prune the parts of the search space that are invalid so that you can basically exhaustively find the statements and the path that eventually leads to the correct one. Right? They have a couple other details here that I think are interesting. For example, here, actually this is more exactly, so they pre-trained a language model on 100 million synthetically generated proofs, and then fine-tune it on a subset of those proofs that require auxiliary constructions, I guess the higher quality versions of those. So out of the 100 million synthetic generated ones, only a small subset of those, roughly 9%, are what kind of like higher quality. So those are they fine-tune on those. But this was another negative here. So look at this. Main results for IMO AG 30s. This is International Math Olympiad, I think Geometry 30, so the 30 problems. AlphaGeometry solves 25 out of the 30. Without pre-training, it solves 21, and without fine-tuning, it solves 23. That is trash. That's telling you that the 100 million synthetic generated proofs used to pre-train the model and then the fine-tuning, all of that work literally just makes you solve 4 more problems. So basically what that's telling me is that the overwhelming majority of the intelligence is coming from basically this combination of a huge amount of brute force search and this symbolic deduction engine. So, I don't know, not particularly powerful, you know? And that's this paper. We might come back to this, but I wanted to end that there. Question from Harsh, what are we looking at today? We're looking at flow engineering. Finding the smallest possible proof, comment from Jay. Yeah, that is something they could have done, right? So I feel like here, right, whenever they fine-tune, right, maybe instead of fine-tune a subset of proofs that require auxiliary constructions, they should have probably taken their 100 million synthetically generated proofs and then filtered them based on the ones that have the lowest number of steps, right? And then fine-tuned on the proofs that have a low number of steps. I think there should have been some way that they force this, some kind of additional forcing function to push it to have less steps, because this is not useful, right? Like being able to solve Euclidean geometry proofs by introducing 100 steps like this, what the fuck are we even doing, right? Like that's not useful, versus something like this, which is human designed, right? Coming up with this idea of like, hey, let's use complex numbers, and now it's way easier. That's what I wish I would have seen out of this paper, right? Is some cool new intuitive thing like that. But really, all this paper showing me is that you can brute force Euclidean geometry proofs. Okay. All right, so the second paper we're going to look at, this is another DeepMind paper, very similar. This is called Mathematical Discoveries from Program Search with Large Language Models. So program search, again, this idea that you're going to be doing this kind of brute force kind of searching, right? But normally when you brute force search, you're picking candidates, right? So you're saying, okay, well, how am I picking the directions that I'm going to search in? If you can pick directions just even slightly better, then everything becomes easier, right? And this is actually what a lot of the chess and Go AIs do, right? Where basically they're doing some amount of search, right? They're doing some amount of like looking ahead, right? The same way that you would in chess, you think to yourself, okay, if I move this pawn here, what are they going to do? And then what ends up happening there, right? So you're doing a little bit of search yourself, but you're filtering the search, right? So you're not searching through the space of all possible moves and all possible enemy moves. It's like you're filtering that space down to, okay, there's 3 moves that I can do, and then I'm going to search down those kind of paths, right? So both of these systems, both the this one here, the Math Olympiad, and then this program search, fundamentally the way that they're using the language model is to generate kind of the limited set of search paths, which then they basically end up doing the more brute forcey kind of search. Okay. But let's go into this one. LLMs, blah, blah, blah. LLMs are cool. Sometimes they hallucinate. Okay, we introduce FunSearch, short for searching in the function space. So a program, you could think of it like a function, right? That's another word for it. So FunSearch comes from function search, searches through functions. An evolutionary procedure based on pairing a pre-trained LLM with a systematic evaluator. The evolutionary part of this is almost like a little bit of a throwaway, to be honest. Like they show it later here. I think they have some drawings to show you exactly what is going on. But I don't feel like it's necessarily a big part of this. It just seems like they just kind of added it there. We demonstrate the effectiveness of this approach to surpass the best known results, pushing the boundary of existing LLM approaches. Applying FunSearch to a central problem in extremal combinatorics, the capset problem, we discover a new set of constructions for large capsets going beyond the best known ones, both in finite, dimensional, and asymptotic cases. So this is their mathematical discoveries. So literally the first two words of the title kind of make you think that they've discovered some fundamental amazing thing, right? And the more you start digging in and you're like, okay, well, what's this mathematical discovery? And the mathematical discovery that they found is some specific solution to a large capset problem. I didn't know what the fuck capset problems were, right? And obviously I'm not like a math PhD, but I feel like I have enough of a math background that if I don't know what these are, they're probably not like super well known, right? So it's like capset problem, very niche kind of problem. Like how much of the total human brain energy juice has been spent trying to find solutions to the capset problem? Probably very small, right? Like I think if you looked over the past 2,000 years, it's probably only been a handful of people for a small set of time who have ever even tried to find solutions to these. So, and then you add to that, in addition, that it's not even, they don't even solve like a low dimensional version of that. The version of this that they solve is a very high dimensional version of that. So that to me just rubs me the wrong way, right? That they're saying mathematical discovery, but the mathematical discovery is an extremely niche problem, and then the very hardest version of that extremely niche problem, but not hard because it's hard because it's basically like this. It's kind of like you need an extreme amount of tedious steps to get to the final solution. And to me, it's not, oh, we've been trying this for thousands of years and no one's ever gotten the solution. It's like no one's ever fucking done this because it's just a huge waste of time to come up with these, to the solution to this capset. So, like I said, I still don't even fully understand this. Like I read this page and I'm just like, what the fuck is this capset? So here it says, a capset is a subset of Zn3, where n is the affine space. So you can see here, this is a two-dimensional affine space. That's why the Z23, right? And then 3 refers to basically the size of the capset. So you're trying to find the largest possible capset, which is like, here it's these 4 points. So here you have 9 points and 12 lines. So if you actually count up the lines here, this is one line. This is another line, 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 and then there's 3 here and then 3 here. So that's 12 total lines. And then those lines intersect to form 12 points. Or sorry, 9 points. And some subset of those 9 points, these 4 specifically, are what's called this capset, right? Which is a subset with no 3 in a line where these objects are simply called caps. Which is like, dude, what the fuck is the purpose of it? Like, what are we doing? You know, like, what is this? Is like the most contrived bullshit like problem I've ever heard, right? And you have like some guy in the 1984 came up with some solution. So this is like before he even had fucking computers. Some person in 1971 who also didn't have powerful computers, and now finally in 2023, oh, we solved it. Like, did you really, or did you just kind of brute force your way to a solution that humans would have eventually figured out if they just had a bunch of time to waste solving this thing? Okay, so I'm shitting a little bit hard on this, but let's look specifically at what FunSearch does. FunSearch is a specification of the problem in the form of an evaluate function, an initial implementation of the function to evolve, and a potential skeleton. Okay, so you have some specification of the problem. At each iteration, FunSearch builds a prompt by combining several programs sampled from the program database, favoring high-scoring ones. So this is kind of the sexual selection part of the evolutionary algorithm, right? So they're calling this an evolutionary procedure. Whenever you're doing an evolutionary procedure, you need basically some amount of mixing, right? So you're providing, evolution has a couple core parts. You need this kind of natural selection, so you need a pressure that basically calls the low-performing things, right? So you need the animals that are not good at this environment, or the functions that are not effectively solving this problem. You want to get rid of those, right? So you need to cull those. That's this evaluation step, right? That's the natural selection step. And then you need this kind of like mixing or basically sex, right? Where like the people at the top, the people that are competent and that are solving the problem, they get together and they create variants of those, right? So they mix the high performers and then get rid of the low performance. And if you have that combination, you do that iteratively, and that's your basic kind of evolutionary process. So the natural selection is coming through the form of this evaluation. The evaluation, much like the math one here, is done by a hard-coded kind of heuristic solver, right? And what that really means is that you can run this Python code, and if it works, it works, and if it doesn't work, it doesn't work. So that's how you're providing the kind of natural selection part, the culling of the low performers. And then the synthesis part, the sex part, where you're actually creating new possible programs, is coming from the LLM. And the LLM is going to basically select two random programs from this database of programs, the high performers, and you're going to basically put them in a prompt together. So you can see here that the prompt has the two random picks, and then you're asking the language model to basically create a new one that is a combination of those two, right? It has a little bit of this, a little bit of that, and then you're going to try that combination. And that's basically this thing. At each iteration, FunSearch builds a prompt by combining several programs sampled from the program database. This prompt is then fed to the pre-trained LLM, and new programs are created. Newly created programs are then scored and stored in the program database, thus closing the loop. The user can at any point retrieve the highest scoring programs discovered so far. Okay. So in order to do this, you basically need to define this skeleton. So here, this is the code for the capset problem, which again, I still don't even fully understand. I think 1D bin packaging, that's a much more easier problem to understand. It's basically bin packing is this problem. You can think of it kind of like Tetris. Like, how do I fit a bunch of things into a bin, right? How do I pack this bin with things that kind of like, they can't overlap, so I have to make sure that they fit nicely, right? Basically, think Tetris in your head, but a 1D version of that. So like a simplified Tetris, right? So this stuff is hard-coded, right? So you create this solving and this evaluation function, right? And then the function that is created by FunSearch is this heuristic, right? So it returns a priority with which we want to add item to each bin. So it's basically returning you could think of it like the position of the little Tetris pieces such that you pack them into that bin. And if you have empty squares, that's bad, right? That's your evaluation, is how many little empty squares in your Tetris do you have. And if it's a very good solution, then you're not going to have any empty squares, right? You can think of it like the Tetris. Everything is packed together super neat, right? So all of this part here is defined by the human, right? So you're defining the problem, you're defining the evaluation function, and you're defining this solver. And the only part that is searched for by this function search is this heuristic, right? So basically, I'm going to introduce a terminology here, and then we're going to look at this terminology in the future papers. But what we're describing here is a new thing which is called flow engineering. So you've heard of prompt engineering. In prompt engineering, you're basically engineering a specific prompt, which is here, this little gray part's here, right? Engineering a prompt such that the language model generates the thing that you want basically immediately, right? It says, I need to figure out a way to phrase this problem such that the LLM generates me the answer, right? That's prompt engineering. Flow engineering is creating a flow of information, a process, a kind of iterative process that you can run over and over and over and over again. And then over time, that iterative process, that flow, creates better and better and better and better solutions, right? So they don't use the terminology flow engineering in this paper, but in later papers, they use this term flow engineering, and I think it's a good way to think about what we're doing here, right? We're creating this evolutionary process, which over time basically iteratively creates better and better programs. Okay. Here I laughed because they call the capset problem a notorious scientific problem, but again, I've never fucking heard of this, and it seems extremely niche. I don't know, maybe some of you on chat are algebraic geometers, but to me, I was just like, dude, this is the most fucking niche thing I've ever heard of. It's like winning gold medal for like the triple jump at the Olympics and then calling yourself the best athlete in the world, right? That's not true at all, right? Like, I'm pretty sure LeBron James can probably beat your triple jump record. It's just that LeBron James never fucking tried the triple jump at the Olympics, right? So this is kind of the problem with this paper to me, is that they keep kind of talking up their solution to this, but it's like, no one's doing this. They're like, the percentage of even math people that are trying to solve this has to be extremely low. Okay. A little bit more information about this. So they're going to be using a language model. The pre-trained language model that they use is Codium, which is an LLM built on top of the Palm 2 model family. So the Palm 2 is basically Google's language models, and then Codium, I guess, is basically a fine-tuned version of those. So Codium is Palm 2 that has been fine-tuned on a large corpus of code and is publicly accessible. Okay. FunSearch relies on sampling from an LLM extensively, right? So you use this LLM to basically do your sexual reproduction, aka take high-performing programs, mix them up, and create new programs. The results in this paper obtained using a total number on the order of 10 to the 6th. We have empirically observed that the results obtained in this paper are not too sensitive to the exact choice of the language model. That, again, is another bad sign, right? So similar to here, right, in this paper, I pointed out that without pre-training and without fine-tuning, right, so just using a generic language model that's just spitting out bullshit, you can get 20 out of 30 problems solved on this International Math Olympiad, which, like I said, to me is indicative of the fact that it's really, you're just brute forcing and relying on the intelligence of this symbolic deduction engine to basically get to the right answer, right? The language model's not necessarily adding much other than maybe kind of reducing that search space a little bit by being a little bit better with its guesses. So we're seeing a similar type of thing here, right? They're saying, hey, it actually doesn't matter what language model you use, because ultimately the juice that you're squeezing out of this is coming from this loop, right? From the fact that you're kind of like iterating and using this evaluation to filter out the bad things. And then whether or not you use a fine-tuned Palm 2 here, or whether you use like a Mistral, not even that. What's the worst language model? A BERT. If you just use a BERT model here and it just kind of like arbitrarily mixes these programs, you'd probably get to the same point, which to me tells you that all the intelligence is coming from this kind of brute force search, not from the actual language model itself. Okay. Blah, blah, blah. Let's see. I think there's a couple other details here which are interesting. Okay, yeah, I thought this was interesting. So the distributed setting enables the running of many evaluator nodes on inexpensive CPU hardware. So the evaluator nodes are the nodes that are doing this, right? So they're the nodes that actually run the program and determine whether it actually solves the problem, right? So in the bin packing, they're the actual computer that actually runs the Tetris and says, okay, I'm going to run this little program that you told me is the best way to pick the rotation of all these little Tetris pieces such that I get optimal bin packing. I don't need a GPU to do that, right? I don't need a GPU. I can basically just do that on a CPU, right? Because the environment is very simple. You can run a chess environment on a Raspberry Pi, right? You can run the actual evaluation for bin packing on only a CPU. It's only the language model, the generative part, or here this what they call it the sampler, right, that actually needs an accelerator or a GPU. So you have a situation where this part here, the language model that receives the prompt and then generates new programs, this part is running on a GPU, and there's a limited amount of them. And then these nodes here are running on a CPU. And this is actually what they do in reinforcement learning as well. So in reinforcement learning, you have a very similar kind of setup, right? So if you're doing reinforcement learning for some kind of simulation, let's say Go or chess, right? You're not using the same computer to run the chess and the Go as you are to actually run the model or the policy and push gradients, right? So you're separating out this kind of rollout episodes, right? The episodes, the rollout, the actually running the simulation and the thing that's actually taking the actions, the actual neural network. So obviously these guys are DeepMind people, so they've been doing this for decades, so they have that same pattern here where they're basically using 15 language models here called samplers and then 150 CPU evaluators. Okay. What else? Here's the result on the CAPSET problem. So remember how in this math Olympiad I was kind of shitting on them for the fact that they're one of their solutions here is literally 110 steps of like complete nonsense. Not complete nonsense, it's all correct nonsense, but it's like fucking ununderstandable like nonsense. Look at this. This is the solution. This is little Python function, right? This is the solution that the language model comes up with. If this, 1. If this, 2. If this, 3. And look at this. It's a giant, like this is, if I was doing a code review and someone gave me this function, I'd be like, please leave and make a better one. Like this is trash. Look at this. What the fuck is this? It's like 50 if-else statements in a row. But why would you end up with this, right? Why would you end up with 50 if-else statements in a row? I think it's coming from the way that this is being done, right? So let's say you generate some programs, and in some of these programs, you have an if statement that works for one particular test case, right? That's going to give you some amount of score, and the evaluator is going to say, okay, this one's mostly wrong, but there's one if statement in there that makes it correct for this particular thing. So it'll end up in this database. And then you'll have some other one that has a different if statement that is right in some other test case. And then that gets added to the program database. So over time, because you're doing this this kind of like, I call it sexual mixing, but it's really this kind of like you're mixing together the ones that perform well. To me, that's kind of a weird forcing function where it forces this kind of if statements, because you're basically accumulating up all the if statements that result in one correct case. So that, I think that the way that that's written is why you end up with these basically solutions that are basically just a ton of these if-else statements, because it's like you're searching through the space of all if statements to find the ones that solve specific test cases, and then the language model is basically just concatenating these if statements, and eventually you get to a point where you've kind of exhaustively created all the if statements that you need to correctly solve this problem. So it's almost like death by if statements. Let's see, you guys have some comments here. People take the main purpose, brute force dull tasks that humans would not want to suffer. Yeah, that's kind of IMO what they're doing here. Discussion. The effectiveness of FunSearch might seem intriguing. We believe LLMs used within FunSearch do not use much context about the problem. The LLM should instead be seen as a source of diverse, syntactically correct programs with occasionally interesting ideas, right? Occasionally interesting ideas being the fact that occasionally they stumble upon an if statement that happens to give them a good answer for some subset of the test cases, right? So, FunSearch is operating in the space of programs, right? So it's really only creating tokens. It's generating tokens that are being put inside this little Python function here, but all the skeleton all around that is better. And in a loose sense, FunSearch attempts to find solutions that have low Kolmogorov complexity. Kolmogorov complexity has popped up a couple times. It's become a kind of popular word now that Ilya talked about it. Ilya is one of the OpenAI scientists, and he mentioned it in a talk of his, and now everybody keeps dropping it in their papers because they think it's awesome. But Kolmogorov complexity is the shortest computer program that produces a given object as output. So it's basically the smaller, like literally, like the less tokens, the better, right? But I think we're starting to get, like, maybe just as a side tangent, one of the things that really annoys me in math is whenever we like people want to obsess over using a specific term that is actually less descriptive than the better way to understand it, right? So if I went to some random computer science person who didn't know what Kolmogorov complexity was, and I asked them, what is Kolmogorov complexity? They would be like, I don't know what that is. And then you say, okay, do you know what the shortest computer program that produces a single given object as output is? And they're like, yeah, I see what that means. I understand what you mean completely, right? If you give someone this sequence here of tokens, they basically completely understand you, right? Versus Kolmogorov complexity here, it's slightly less tokens, very slightly less, right? Rather than basically whatever this is, like 10 words, it's 2 words. But now you're forcing everyone to store this particular set of tokens in their head as basically just a pointer to this set of tokens, right? And I just find that it just drives me insane because I'm like, dude, literally you take this sentence here and then just get rid of this part here, right? Imagine this sentence, but instead of it just said, in a loose sense, FunSearch attempts to find solutions that are the shortest possible program that gives a given object as output. There you go. Now you basically transmitted the same information, but without having to use this fucking new terminology that now everybody has to remember, right? And I don't know, that's just a pet peeve of mine because like too much brain power is wasted storing these names from old dead white guys rather than storing the important part, which is the actual concept, right? Just have people store the concept and describe things in terms of like actual like understandable tokens. Like stop creating these fucking new tokens, right? The reason people create these tokens is because people have egos and they want their name associated, right? They want to go to a little piece of land and they want to put their flag down and they want to, for the future, for the rest of the future, people, they want their name to be there, right? They want to build that monument in stone so that people remember their name. But we're not in the business of fucking remembering people's names, right? I don't care about the greatness of this man called Kolmogorov. I'm sure he was intelligent, but my interest is in fucking learning things, not in remembering these names. Okay, tangent over, but that's just something that always peeves me is like the insistence on using these terms for things that are kind of better understood or better described through a pretty short sequence anyways. Okay. Question, is this Kolmo nothing on the AST or the text? I think it's just straight text, but they do say it's loosely that, right? In a loose sense, right? But search implicitly encourages concise programs. Yes, but no, right? Because think about this. Is this a concise program? Right? Not really, right? It's not very concise. So I think that sure, search encourages short programs because the short programs, you find them faster, right? So if you're searching through the space of all possible moves in a chess game for the ones that give you the final win, right, the checkmate, you're going to find the checkmates that only take a couple moves before all the other ones, right? So you're going to find the short ones before you find the long ones. But in this case, the kind of evolutionary algorithm that kind of mixes, this mixing here, I think destroys that, right? Because I don't have a way to prove it, but I think that this mixing, right, and the fact that you're mixing these together, that's providing this kind of selection pressure for compositionality and kind of like modularity, right? So because you're doing this mixing and then evaluating the mixed ones, it provides this pressure for algorithms that are able to basically have subparts that are good, right? So for example, maybe one algorithm only had this statement here and everything else was trash. But because it only had that one if statement, that means that whenever it gets mixed with a different program that also has a different if statement, maybe this one here, their combination, right, by both of them being a little bit more modular, you can compose them together and create a better program. So I think the evolutionary part of this kind of removes any of the stuff they're talking about here where search implicitly encourages concise programs. So I don't actually think that this particular FunSearch flow is directly finding programs with the lowest Kolmogorov complexity, right? I think that there's other parts of this that are almost moving in an opposite direction. So I don't know. I would challenge that. What else? I think there's here they talk about the implementation. Samples K programs to encourage LLMs to merge ideas from them, right? This is this like kind of compositionality and modularity kind of forcing function that I see. I think this is a nice little diagram. So this is in the appendix section. This is the evolutionary method. The initial programs are separated into islands, and each of them is evolved separately. After a number of iterations, the islands with the worst score are wiped, and the best programs from the island are replaced in the empty islands. So this is kind of the natural selection, right, where you wipe out the low performers, and then you kind of mix the high performers. So that's just kind of like a basic evolution process. Program clusters within islands. We first sample clusters favoring the ones with higher score. Within the chosen clusters, we sample a program favoring shorter programs. So maybe this. Maybe here there's a little bit of a regularizer, so they do add some explicit regularization to kind of programs that have less tokens. So there is a little bit of a hard force there. Sampled programs are used to prompt the LLM, which generates a new program. This is what I call sex. And then if a new program is correct, it's added to the island, either in an existing cluster or a new one if its signature was not yet present. Okay, and that's basically it, guys. That's this paper. This is Mathematical Discoveries from Program Search with Large Language Models. So far, we've basically gone to two DeepMind papers, which are basically very similar. What they're doing is they're using a language model to generate possible search directions in what is largely a flow that is basically kind of like a brute force search. So they're brute force searching over all possible solutions. And this one is in this kind of programming language of Euclidean geometry proof. So this is basically, you could think of it like a programming language, right? There's like a formal definition of the types of deductions and syntax that you can have, right? Such as saying, okay, well, there's a midpoint between BH, right? There's a formal syntax to this that can be evaluated by an external evaluator, right? That can run on a CPU. So here it's this kind of algebraic kind of math language, but here in this one it's basically Python. So both of these DeepMind papers are effectively just doing search, but they're filtering the search directions with an LLM. So not filtering, but they're basically choosing which directions to search in via an LLM. This one has the extra kind of like evolutionary stuff, but I don't feel like they necessarily needed to do that, right? They could have just said instead here, pick the top three or pick the top one and then just create a new variant of that or something like that, right? They didn't need this kind of mixing stuff that they do there. But that's basically those two papers. And now we're going to go to this paper. So I think this is the best paper out of all of them today. Maybe not. Maybe the last one that we're going to look at is better, but this one is pretty good. So this is called Code Generation with AlphaCodium, from Prompt Engineering to Flow Engineering. And here is the kind of official flow engineering. This is like the new terminology that I think if you guys come out with anything today, it's this idea of flow engineering. So flow engineering is creating these flows, or this kind of like set of processes, these kind of like do this and then this and then this and then this, and then ideally they loop back in such a way, right? These graphs are cyclic in such a way that you can basically iteratively run them over and over and over again, right? And just to hype you guys up on this paper was brought up by Andrej Karpathy, another very famous researcher at OpenAI. So prompt engineering, or rather flow engineering, intensifies for code generation. Great paper reading and a reminder of how much alpha there is. So alpha is actually a term that comes from, I think, the finance world. So in the finance world, alpha is basically signal that you can extract to your benefit, right? So if you Alpha is your ability to extract signal that is going to improve your performance. In finance, that basically just means make more money, but here it basically means creating good code. So Andre is here, what he's saying is that you can get a bunch of performance improvement. Here, for example, you have 19% generating correct code 90% of the time versus 44% of the time, so a big improvement. Pass at 5 basically means that you're generating 5 and then picking the best one out of those. In moving from a naive prompt answer paradigm, so the naive prompt answer paradigm, this is kind of what prompt engineering is, right? This is you type your problem and the language model has to generate the answer in one shot, or maybe you're doing prompt answer but at 5. So you get the LLM just directly generates the answer. You run it 5 times, it generates 5's answer, and then you pick the best one out of those. To a flow paradigm. Flow paradigm is when you're doing this process where you're creating a kind of like a graph that has some cyclic kind of part, so you can run it iteratively and then eventually get to the final answer. But the final answer that you get from that is going to be significantly better than if you were just to sit there and try to find better and better prompts to get your prompt answer to work, right? So we're kind of moving away from this prompt engineering to this idea of flow engineering. Okay, so and once you think about flow engineering, you realize that these two papers are flow engineering. That's what they're doing. This is a flow engineering paper, and this is another flow engineering paper, right? Both of these DeepMind papers, they don't use this term, but that's what they are. Okay, let's read this abstract. Code generation problems differ from common natural language problems. They require matching the exact syntax of the language, of the target language. So you need to be very, very precise in the tokens that you use with code. You can't just kind of, it's not like poetry, you know? I guess haikus are probably more like code because you have to be exact. Identifying happy paths, edge cases, paying attention, addressing other code-specific issues. Many of these optimizations and tricks have been successful in natural language, may not be effective for code. We introduce AlphaCodium, a test-based, multi-stage, code-oriented, iterative flow. So test-based is a reference to how they're going to do this. And for those of you that are kind of programmers or coders, you might have heard of test-driven development. And this is basically what the core idea of this is, that is effectively test-driven development. And maybe let's finish this and then we'll describe what that is. Multi-stage, right, it's iterative, and then code-oriented iterative flow. They test AlphaCodium on a benchmark called Code Contest, which is basically competitive programming problems, so like LeetCodes, codes, basically. The GPT-4 accuracy, right, but because this is a flow, it's not specific to a language model. You can use any language model in this, right, which is effectively what they found in this other paper. If you remember in this one here, right, they said it. They said the results obtained are not too sensitive to the exact choice of a language model. So the magic with the flow engineering is that if you come up with a flow that works well for one model, as soon as they release GPT-5, it's also going to work well for GPT-5. So the flow is does not depend on the language model, and you can swap out the language model as you want, which is pretty good because if you're building a product, right, you can now design your flow, and then you can switch API providers. So you could use GPT-4. GPT-4 suddenly becomes very expensive. Doesn't matter. Most of your juice, most of your intelligence, most of your performance is coming from the flow that you designed, not from the API provider, not from the model, not from the language model itself, right? So I think there's a lot of kind of ramifications for the future when we think about flow engineering as opposed to prompt engineering. Okay, so they get this 44% to 19% improvement, so quite good. Here, this is AlphaCode is kind of an older, more prompt answer kind of prompt engineering language model, classic language model, if you want to think of it. That's how fast machine learning moves, that we're calling, there's such a thing as classic language models now. So AlphaCode is a classic language model in that it writes code, but it writes code in this kind of prompt answer type style where you basically have to engineer the prompt such that it produces the right answer, and you don't do any kind of fancy flow. It's basically just kind of brute force, crank out 5 answers, and then hopefully that one of your answers is in that. Illustrations of the AlphaCodium flow. The model struggles to solve code problems with direct prompt, which is when you just prompt it and it gives you the answer. Iterating on public tests stabilizes and improves the solution but leaves blind spots because the public's tests are not comprehensive. A full AlphaCodium flow, which includes a pre-processing phase as well as iteration on AI-generated tests, allows the solution to be further improved, leading to increased solve ratio. Okay, so here you have a low-dimensional representation of the problem space. So obviously the space that these coding problems are in is extremely high-dimensional, very difficult for us to think about, but here is a kind of a two-dimensional version to build an intuition, right? And what you could think of is here is that there's some subset of the code space, right? All possible programs that are a correct solution to the problem, right? There's a lot of those. And those are all within this blue cloud, right? So there's some subset of all possible code, all possible programs that solve this. The solution represented by the generated code. So the LLM is going to generate some solution that exists in this red cloud, right? So you want a solution that is generated by the LLM that is within the blue cloud, right? You want something that is actually a correct solution and that is generated by the LLM. So the overlap of those two. Well, what do we know? Well, we know that if you write a test, right, a test case, like a little test function, test, think of it when you write a leak code, right, there's these tests that you're comparing against, right? And those tests are basically, okay, if I give you a value of 0 and a value of 1, this is what the answer should be, and you should get the right answer, right? So you can come up with a bunch of weird test cases, right, that based on the problem itself. So you can see how all of the test cases, right, are within the overlapped region, right, because the test needs to work. So these are the public tests, which basically is tests that are written by a human. And the insight that they're going to have in this entire paper is that generating additional tests is easier than generating a correct code solution, right? So basically what they're saying is it's easier to come up with new tests than it is to come up with a full solution, right? So something like AlphaCode is coming up with a full solution just one shot, boom, just creates the solution based on your prompt. But what they're doing here is they're first going to generate more tests, right? So you're going to say, okay, here's my problem description, and then here are some public tests, here are some green dots. The first thing that the LLM is going to do is it's going to think about the problem, then it's going to think about what other public tests it can create, and then it's going to basically generate tests. So this is what I mean by test-driven development. You can actually do this as a human. So sometimes when you're designing a new feature as part of a software engineering team, rather than kind of going right away and designing that feature, you start by basically writing tests. So you say, okay, well, what are some test cases for this new feature that I can write down? And then once I write down those tests, it'll be very easy for me to iterate on a solution, because once I start writing a little bit of my solution, I can always run it and see if it solves all the tests that I came up with, right? And this is known as test-driven development. And here, what AlphaCodium is doing is it's basically doing that, but with a language model. So the AI is generating these tests, right? And then the more you generate those tests, the easier it's going to be to basically generate a solution that you can then check against all those tests. And then if it works with all the tests, you know that it's in this overlapped space, which is the space that contains correct solutions to the problem. And that's kind of like really, I think, the core idea of this paper, and really the best idea. There's other parts to this flow. So the problem reflection, the ranking solutions, generate additional AI tests, initial code solution. You see this loop here because it basically keeps testing against these tests. Iterate on public tests, iterate on AI tests, and eventually you can run this. You see these cycles. This cycles means you can just keep running this iteratively, and eventually you end up with a final solution that is ideally somewhere in this overlap, right? It is a correct solution to the problem. They do this on the code contest dataset. Instead of training a dedicated model, we focus on developing a code-oriented flow that can be applied to any LLM, which again I think is a bigger deal than people think it is, right? Because what we're learning is that prompt engineering is fragile. Prompt engineering is LLM specific, right? So if you come up with a cool prompt that works for GPT-4, that cool prompt might not work for Llama 3, right? It might not work for Llama 4. It might not work for GPT-5, right? So prompt engineering is like inherently fragile in that way. Flow engineering is not. Flow engineering is very robust to that, right? If you design a flow, you can swap out the AI and it'll still work. It'll probably work better. So if you guys are making any startups, make sure you're making flows, not prompt engineering. Okay. And the other ramifications of that is that it pushes the API providers down. So think about it this way. Docker containers make it easier to run your compute workload on a variety of hardware and a variety of cloud solution providers. So if you have a particular compute workload and you put it in a Docker container, you can run that Docker container on GCP. And then GCP starts saying, hey, we want more money. And you can be like, all right, fuck you. I'm going to go to AWS. And because you have it inside a Docker container, it's pretty easy to run it on AWS now, right? You don't have to spend that much time. Of course, you have to spend some time, but it's easier to switch, right? So containerization was a force to basically commoditize the cloud solution providers. Flow engineering, in the same way, is a force to commoditize the API providers, right? The language model providers, the raw base foundation model providers. So the more startups that use something like flow engineering to create a genuine novel product and kind of experience, if they can just swap out GPT-5 to Llama 4, that means that GPT-5 doesn't have this kind of like lock-in, right? It has to basically price itself competitively in order for the people to continue to use it. So I think this has implications for the market of AI that aren't necessarily mentioned in this paper because this is more of a technical paper, but okay. Generating additional data in the pre-processing stage, such as self-reflection and public test reasoning to aid it with the iterative process. This is the first part of this flow here, this problem reflection part, which is not generating tests. It's basically like the problem description. They want you to just be able to type it in like one sentence or two sentences. So this problem reflection just kind of like it's kind of like an internal chain of thought to just make it more fleshed out, right? So I think they have some examples here, but yeah, this is the problem description. So kind of like hard to parse, maybe kind of confusing. The self-reflection, which is the first part of this flow, kind of like creates easier kind of bullet points, kind of like makes it a little bit easier for the language model to then generate these tests. So these are the public tests, like kind of like elite code. These are the ones that you write as the human, right? And then these are the tests that are generated by the AI, right? So the AI is basically doing test-driven development from its own self-reflection of the original problem. Public test reasoning, explain why each test leads to the output, generate possible solutions, rank these solutions, generate additional AI tests, and so on. And then now you can just run this, iterate on the code solution, iterate on public tests, add more tests, add more tests, add more tests, add more tests. And again, it's kind of similar to this here, but the reason this works is because you can always verify these tests, right? So the fact that when you iterate on these public tests, you can actually plug them in, right? You can actually plug in these values into your solutions and verify that they're correct, right? So it's like, again, the whole reason this works is because you have that ability to actually say this actually works and this actually does not work, right? So you can actually verify that. You have, much like chess, much like Go, much like Euclidean geometry, and Python, all of those things have that ability in common where you can actually, you can run it out, you can evaluate it, and you can get a 0 or a 1. 0 does not work, 1 it works, right? And all of these solutions, like if you took that part out, they're fucked, right? They need that ability to actually say this is correct. The flow relies on knowledge accumulation, trying to progress from easy to hard. This is kind of they're kind of trying to make you think of something like curriculum learning, right? Where the LLM is in this flow, it's kind of creating its own curriculum, right? It's adding more tests. the more tests it has, the more reasoning points it has. It's able to kind of maybe think of more complicated tests. So it has this kind of like natural curriculum learning kind of flavor where it's generating easy ones, then harder ones, then harder ones, then harder ones, and so on. The key insight, again, is this idea behind test-driven development, which human developers figured out a very long time ago, that generating tests is easier than generating the code. Some interesting things from this paper, which I think this paper was already pretty good, but then they do a couple awesome things here. They tell you some interesting things that they came up with, which I think bring it from being a cool paper to an awesome paper. So one thing that they talk about is that YAML, the usage of structured output, asking the model to generate an output in YAML format equivalent to a given Pydantic class, is a key component in our proposed flow. This is more of a prompt engineering thing. So this is kind of like a little hack, but it's a prompt engineering hack, but it works, right? So they say that YAML output is far better for code generation. Generated code often contains single quote, double quote, special characters, and so on. LLMs will struggle to validly place these characters inside a JSON format. So it's interesting how JSON has more shit. So JSON, you see how you basically need to have these brackets, you need to have these commas. The benefit to that is that JSON doesn't matter about the indenting, right? You can basically the JSON could just be one giant line of text and it would still work. But YAML, which is a different kind of markup language, it does rely on the indenting, right? So you do need to indent everything correctly, but because of that, you don't need these brackets, right? So it's basically the difference between something like C++, where you do need these brackets, and something like Python, where the indenting removes the need for brackets. And here, they basically ran a little experiment for you, and they said, okay, well, we tried JSON and YAML's better for that, which is super interesting to me because that's the exact same reason YAML is better for humans, right? Like, why do people prefer to use YAML over JSON? Because there's just less shit to write. You don't need to write these brackets. It's easier to read, and that ends up being the exact same reason why it's better for language models, which is beautiful, right? Which this paper is just beautiful in that way that test-driven development, humans figured that one out because it's easier to write tests than it is to write the solution. Turns out, same thing can be said for LLMs. YAML was created because JSON was really annoying to type. Turns out, it's also true for LLM. So all these little tricks and tips that were basically the result of humans coming up with a solution that helps humans are also helping LLMs, which, I'm not one to try to anthropomorphize language models, but it seems like that's a vector for possible research ideas, is take something which was done for the purposes of making it easier to understand for humans or solving something that humans do it in some specific way, and then just treat LLMs as if they were humans. And then it works. Like, it actually, it's a valid, here's the experiment to prove it, right? YAML's better than JSON. Okay. We were looking at some of the stuff that they mentioned here, some of the other insights. When asking an LLM to reason about an issue, better results are obtained when demanding the output to be in bullet points. Again, this same kind of idea of like, why do humans use bullet points? Because it's easier to read. Well, if it's easier to read for the human, it's probably easier to read for the language model too. Bullet points encourage an in-depth understanding, force the model to divide the output into logical. It's like all of these are like exactly what you would say for a human. LLMs do better than generating a modular code. When LLMs are asked to generate a single lengthy function, we observed poor results, right? So if you go into GPT and you say, hey, generate this giant like 700 line code for me or program for me that has like 10 different functions in it, it's probably not going to get it in the first try. But if you have kind of more of this flow based idea where you kind of do each of them individually, right? It's better. So LLMs are better at generating modular code, which again, you could have inferred from the fact that humans are better at generating modular code. Soft decisions with double validation. LLMs tend to struggle with code tasks that require them to think, reason, and make strict, non-trivial decisions. Doesn't that sound like humans? Let's take, for example, the task of generating additional tests. Some of the tests the model generate will be plain wrong. With the double validation process, we add an extra step where, given the generated output, the model is asked to regenerate the same output but correct if needed. We found that this step of double validation, while encouraging the model to be critical and reason, is more effective than asking a direct yes or no question. So another kind of cool little trick that you can take into your own world, right? Asking the AI model to regenerate an answer is going to make it give the correct answer more often than not, as opposed to just saying, is that correct? Right? So kind of a simple yes and no question is going to result in less performance than if you were to basically say, hey, generate that code again and see if you can find any bugs when you regenerate it. Try to avoid direct questions and leave room for exploration. We adopt a flow of gradual data accumulation from easier tasks to hard ones. This kind of curriculum, kind of learning analogy that they're trying to do here. But again, you could also apply this to humans, right? Humans are probably, when you're trying to get it, like if you're managing people, it's better to leave room for exploration, right? Like if you're managing software engineers, you don't want to tell them exactly the way to do things. You want to basically give them some goal, but then give them the ability to kind of orthogonally move to the kind of direction that you gave them, right? So you're saying, hey, do this thing, but you can do it however you want, right? And that actually ends up being a better management strategy than saying, here's the exact thing you need to do, and these are the 10 steps that you need to do to get to that thing, right? Nobody likes dealing with those kind of managers, and turns out that language models also have the same thing, where give the language model a little bit of room to explore and come up with a novel path to that final solution. This is the pydantic definition. So I've actually used this myself. So when I was working on that humanoid robot, I defined some of the objects that I had, such as a pose and a look direction and a movement, right? Like these kind of like object-oriented concepts that I wanted the language model to be able to understand. I wrote them in the prompt as a class like this, right? And that's exactly what they're doing here, right? Pydantic is like the actual format here. This is almost like a data class, but like third party. And by providing it in this kind of code format, this is basically prompt engineering. The language model has a better chance of understanding it. And that's, I think, most of this paper. Let's see. AlphaCode uses a different generation methodology. So they're comparing to AlphaCode. AlphaCode is the DeepMind, basically fine-tuned language model. So pass at 10 at 1K. That's a little weird, right? You probably know what pass at 5 means. Pass at 5 means that GPT-4 gets 5 tries to solve the solution, or to solve this particular coding problem, and you pick the best one out of those 5. So it's kind of like the top 5 or top K classification accuracy, right? Where you're picking the best guesses, and then out of those 5, if the correct one is in those 5, you count it as a pass, right? So pass at 10 means it gets 10 tries, but what the fuck does pass at 10 at 1K mean? So they tell you here, AlphaCode uses a different generation methodology, fine-tuning an unknown model specifically for code problems, generating a very large number of code solutions, clustering them, and submitting K solutions from the top clusters. Pass at 10 at 100K, for example, means the 100K solutions generated and clustered, and 10 solutions were finally chosen and submitted. So if you thought pass at 5 was cheating, pass at 10 at 100K is like uber cheating. It's like you're basically, imagine a leak code problem where you get 100K solutions, 100K attempts to pick the right solution, which is just way too much, right? But the number here that is worth looking at is this one here, right? Where no matter what LLM you use, right, this AlphaCodium flow is way better than direct prompting. So you're going to end up in a better solution. 29% pass at 5 versus 12% pass at 5 if you were just to directly prompt. 17% versus 8%. 24% versus 12%, right? And that's regardless of the language model you're using. It's always basically almost doubling the performance, which is powerful, right? Because it means that you, as a startup, as Codium AI, the startup, you can create this flow and you can give a product to people, and you're no longer beholden to the LLM provider because you're not fine-tuning it, you're not doing anything. You're basically just using it as is, zero shot, and then really the intelligence is all in your flow. So flow engineering is the hot word. That's the word to remember, and that's the word to mention to the VCs when you try to raise money. Cool. So that's this paper, Codium AI, flow engineering, and we're going to move to the last paper. So let me take another sip of my coffee here, blow my nose, and I'll do this last paper. All right. Sounds like flow engineering is just slapping a label on the next iteration of chain of thought, tree of thought. Yeah, chain of thought, tree of thought, those are basically the same thing, right? There's a lot, like I said, it's all, terminology can get kind of, don't get too bogged down, right? It's kind of like the rant that I went on here on Kolmogorov complexity. Like, right, you could say the same thing about flow engineering, right? It's like you know what flow engineering is. You know what chain of thought is. You know what tree of thought is. You have an intuition for what those mean. You just might not know the exact word flow engineering. So someone might mention to you, like, hey, what do you think about flow engineering? And you're like, I don't know. I've never heard that. And then they're like, wow, you must not know fucking anything. And it's like, no. It's just they don't know what flow engineering means. But they know what chain of thought is. They know this idea of passing at 5. They know this idea of multi-shot, right? Like, it's all kind of the same ideas, but people just come up with different words for them. And all you really need to know is the underlying kind of concept. And the concept is basically these flows of information that are agnostic to the language model that basically iteratively improve the solution to something that has this ability to be externally validated, right? So ability to be externally validated, code, games like chess and go, any kind of formal language like math, geometry. Okay, but it's already 9:30, so we got half an hour here. Let's do self-rewarding language models. This is a paper out of Meta. This one has also been kind of making the rounds in social media because I think this one is kind of how we get artificial superintelligence. And with that hype, let's kind of start with this abstract. We posit that to achieve superhuman agents, future models require superhuman feedback in order to provide an adequate training signal, right? This is this idea that you need some kind of signal that you can farm for information to improve your intelligence, right? You need that reward signal from the chess or the go, the I won the game, I didn't win the game, or the external evaluator that tells you that your program works or it doesn't work, right? It's like you need that training signal, right? Commonly current approaches train reward models from human preferences, right? So the way that we do RLHF is we're basically giving a language model like the 20 games of Magnus Carlsen, and then we're saying, copy that, mimic these Magnus Carlsen games, right? But then what the language model is kind of doing is it's really just mimicking that thing that you gave it, right? It's just kind of imitating Magnus Carlsen rather than figuring out a way to achieve superhuman chess performance, which is what you get from farming that kind of environment reward signal. Okay. I'm kind of making loose analogies here, so don't crucify me if I say something weird. Which are then bottlenecked by human performance. These separate frozen reward models cannot learn to improve during LLM training. The frozen reward models are the value functions or the Q functions, the neural networks that basically learn that this is what you do in RLHF. This is what you do in a lot of reinforcement learning is you're learning these neural networks that approximate the reward. We study self-rewarding language models where the language model itself is the reward. So the LLM is generating the output, and then it's also judging its own output. LLM as a judge, prompting to provide its own rewards during training. We show that during iterative DPO training, DPO is direct preference optimization. It's kind of like the cool kid RLHF now. It's just an RL algorithm where you can basically fine-tune a model on a set of solutions. And here's I think they have the exact definition of what you need. Let me see. Yeah. So in order to do DPO, you need these instruction prompt response. Actually, that's not the one you need. Let me see. Where is it? Basically, you need the prompt, and then you need a good one and then a bad one. I don't have it here. It's somewhere in here. I just don't know where I highlighted it. But basically, to do DPO, you need this kind of fine-tuning data set that has, here's the original prompt, here's a response to that prompt that's good, and then here's a response to that prompt that's bad, right? You need those little 3 tuples in order to do this DPO. Also, the ability to improve using high-quality rewards. They use Llama 270B on 3 iterations. Our approach yields a model that outperforms many existing systems, including Claude 2, Gemini Pro, and GPT-4. While only a preliminary study, this work opens the door to the possibility of models that can continually improve. Right? The model gets better over time, and that's how you get superhuman AGI. And the reason people are fawning over this paper is here in Table 1. 3 iterations of this self-reward loop with DPO gets you a win rate of 20%, which is better than GPT-4. And that's it, guys. We're already beating GPT-4 by taking a Llama 2 70B and having it judge its own outputs, fine-tune on the judged outputs, and then repeat that 3 times. Pretty good. Okay, let's maybe go to this figure 1 because I think this is all you really need. This is not a very complicated concept. It's actually a very simple concept. So here we go. Self-rewarding language models. Our self-alignment method, the LLM is aligning itself. It's both the actor and the critic. Method consists of 2 steps. Self-instruction creation. Newly created prompts are used to generate candidate responses from the model MT. So you generate some prompts. This is the same model, so basically MT is the same model as MT plus 1. It's just that it's 1 iteration ahead, right? So every time you get to the end here, you then feed that fine-tuned model back to the original here, and then you run it again. This model generates responses, right? So here's the response to the prompt. X is the input, Y is the output. Then that same MT model generates the rewards, right? So it's basically saying, is this a good response or is this a bad response? And then you pick YIW, YIL. This is the triplet. This is the triplet that you need for DPO. So in DPO, you need basically what are called preference pairs, which is basically given this input XI, I have some output YIW and then some output YIL, where W is the win and L is the loss. So you're basically saying, for this prompt, this is the output that I like, and this is the output that I didn't like, right? And then you basically just run DPO on that, fine-tune on that, get a new model. And then you go all the way back here, and you do it again. Predicts its own rewards here, the MT, right? You're using the same model to basically pick YIW and YIL, picks the winner and loser. Preference pairs are selected from the generated data, which are used for training via DPO, resulting in the model T plus 1. This whole procedure can be iterated, right? So you run this, it's a flow, resulting in both improved instruction following and reward modeling ability. So it's not like the model just gets better at being an actor, right? Generative, but it gets better at being a critic or a discriminator, right? So this pattern has been seen many times, right? In a generative adversarial network, you have this idea of a generator and a discriminator. In a GAN, they're separate, right? Separate network for the generator, separate network for the discriminator. In actor-critic reinforcement learning, you again have the same idea. You have an actor, which is the policy, which is going to be a separate network to the critic, which is the value function, right? But in this paper, the self-rewarding language models, they're both the same. The generator is the discriminator. The actor is the critic. You're using the same language model for both of those. And it works, which is the magic. And this is huge because the hard part about actor-critic or generator-discriminator in a GAN is that training that is difficult because you're creating this kind of adversarial relationship where they need to be in tandem, right? It's like you can't get good by playing Magnus Carlsen over and over again, right? You need to kind of play against someone who's kind of at your level, so that like balancing those out is difficult. That's why training again is difficult. Actor Critic is difficult. But here, you kind of get a free solution to that. The free solution to that is when you do DPO on these preference pairs, this MT+1 is a better generator, but then it's also a better discriminator. So it has better reward modeling and it has better instruction following. So because you get that for free, this is basically an infinite flywheel. Okay. They use Llama 270B, and interesting here, they use the Open Assistant dataset. Open Assistant is the dataset that was created by a YouTuber called Yannick Kilcher. I don't actually know if that's the way you pronounce his last name. I don't know if I've ever even heard his last name, but pretty famous machine learning YouTuber, and he created basically Open Assistant. I think they closed it, so they stopped working on it, obviously because they don't have infinite money. They can't really compete against these solution providers, but part of the fruits of the labor that they did there was they created a data set for instruction tuning, and this is the Open Assistant data set. So interesting that the people at Meta AI are using a YouTuber data set to start or seed their research here, which is kind of cool. Importantly, the reward modeling ability, which is no longer fixed, improves as well, right? This is the detail that makes this very powerful. While this effect likely saturates in real-world settings, it provides the intriguing possibility of obtaining reward models and hence LLMs that are superior to ones that could have been trained from original human-authored seed data alone. So here they're basically saying the reward models, so if you're doing RLHF, you're basically getting some original human-authored seed data, right? Like a bunch of people in Nigeria are basically creating this RLHF data set, and then you train the reward model on that RLHF data set. That's how RLHF works, right? But here they're saying, hey, the LLM itself is capable of creating its own reward model that is better than what you would get if you were to go to Nigeria and get 100 people in a warehouse to label an instruction tuning data set. So Scale AI in shambles, because that's kind of Scale AI's MO, is using impoverished people to enrich the tech elite. Seed instruction following data, seed set of human-authored instruction prompt response, general instruction following examples. This is where they're going to use the Open Assistant. Seed LLM as a judge, instruction following data set. We assume we are provided with a seed set, evaluation instruction prompt, evaluation result response, which can be also used for training. So seed is just the first time that they use it, but then in subsequent iterative loops, they're going to be using the instruction set that's generated by their own model. Self-instruction creation, generate a new prompt using few-shot prompting, sampling prompts from the original seed IFT instruction fine-tuning data set, following the approach of blah, blah, blah. Then you generate candidate responses, generate n diverse candidate responses for the given prompt, and then you evaluate them. So then the same language model that generated these responses is going to then score them from 0 to 5, and then basically that allows you to create these triplets where you have a high scoring response and then a low scoring response. What else? There's not much to this paper. Like I said, it's a relatively simple concept. It's just the fact that it works is very powerful. We sample n equals 4 candidate responses. So here's the temperature that they're using. Gives you an idea for the size of these instruction tuning data sets. It's roughly 4,000 preference pairs and then 6,000 preference pairs for the second iteration. So this is not a lot. It's just like 8,000, like less than 10,000 examples. But I feel like this is something where they could have tried a little bit more, right? One of the reasons that RLHF and other instruction tuning data sets are in the order of single-digit thousands is because someone has to make them, right? So why do human-authored instruction data sets why are they usually around this many? It's because someone, like, that's kind of the limit of what you can create with humans, right? But because you're synthetically generating these data sets with the LLM themselves, why don't you try 100,000, right? I feel like that's something that I feel like I wish I would have seen in this paper is like, now that you're automatically generating these AI fine-tuning data sets, what happens if you 10x that? Make it 60,000, make it 600,000. Does that make it better or worse, right? Like I would have loved to see like an extra level of scale here now that they can automatically generate these. Here you get kind of the results. So this is figure 3. Ability improves with self-train. So self-rewarding model. You can see over time, this is M1 is the first iteration, M2 is the second iteration, M3 is the third iteration. You can see it's getting better and better over time, right? This is the alpaca style leaderboards. Alpaca eval, which is basically you're using GPT-4 to pick the best solution. So GPT-4 picks, it basically says, okay, here's the prompt left, prompt right. Which one do you want? And it doesn't know which is which, right? And they swap the order because the order matters. But that's also the one part of this paper that is a little bit dubious, right? So this number, this score, this benchmark that they got here where they beat GPT-4, that is GPT-4. That's according to GPT-4. According to GPT-4, our self-rewarding loop results in a better model. But what does that mean, right? What exactly does that mean? And they too talk about this, right, where there could be a problem here, right? While we have evaluated our models using GPT-4 using head-to-head and Alpaca 2 leaderboard style, there are many other automatic that one can measure. We observed an increase in length in model generations, and that's like, ooh, red flag. There is a known correlation between length and estimated quality, which is a topic that could be understood more deeply and in our results particularly as well. It could be the case that what these language models are doing is they're basically reward hacking, where because you're ultimately evaluating this final thing here, this MT plus 1, and then MT plus 2, and then MT, like you're over this iterative process, you're ultimately just using GPT-4 to evaluate this. So it could be the case that what your language model is doing is it's just discovering some reward hacky way to increase reward, right? And maybe it's just the length of the response, right? Maybe it's the specific words. Maybe it uses bigger words. Maybe it uses more concise words, right? And we're starting to get into very murky territory here when we're using LLMs to evaluate other LLMs where we don't really understand why GPT-4 picks the left or over the right, right? It's like you don't really know. And there's probably some hidden shit underneath that we don't understand, right? Where maybe GPT-4 really, really likes it when you use a specific token as the fourth word in a sentence, right? And then what this self-rewarding model is figuring out, it's saying, oh, that third token, it's really great when I make it a word that starts with the letter Q, right? Or something weird like that. And that's a potential kind of red flag here, is that it's very difficult to actually know what improvement means on a prompt, right? It's like, I think they actually mention it here, but it's like this effect likely saturates in a real-world setting. We're like, what are we actually improving when we're just looking at kind of like generic language, right? Like you're answering a generic question. What does it mean to get better at answering that question, right? At some point it saturates, right? It's like, imagine if you were trying to get a language model to maximize the best response to like, is a pineapple a vegetable? Right? Like, what is the best response there? Is the best response just no? Is the best response no, comma, a pineapple is a blah, blah, blah fruit? And it's like, you know, so I'm saying it's like there's a saturation there where like for a lot of the tasks that we want these language models to do, it's not entirely clear how these answers are being judged by these LLMs. And it could be the case that it seems like we're getting better and better responses, but really what we're getting is like we're improving in a dimension that doesn't even matter to us as humans. And GPT-4 is basically saying, okay, well, when you answer the question, is a pineapple a vegetable? I want a solution that is like a haiku, but like a weird type of haiku that I can't even identify as a human, but GPT-4 sees it and says, wow, look at that answer. That's the haiku that I was looking for, right? So I don't know, just something to think about there, where I think this type of self-reward is going to be very big for kind of tasks like this, like coding, or what are they doing here? Programs, function search, or algebraic proofs, right? Something where the actual LLM can probably judge the content, but for tasks that are a little bit more nebulous, it's not entirely clear to me that you're at some point better at modeling the reward, because the reward might actually be some nonsense that doesn't actually matter to us as humans, right? Okay. But that's basically this paper. Pretty cool little paper. This is actually at the very end here. They have the LLM as a judge prompt. A little bit of prompt engineering for you guys here. This is a pattern that I've started using a lot as well. This is like comes from HTML, where you basically have open bracket or alligator mouth, other alligator mouth, and then dash. This basically means end of this section. Right? I've seen this used time and time again. So like if you have a prompt that you're doing and there's like things like this where it's like response here, or like you want to separate out parts of things without confusing the LLM, a little prompt engineering hack here is to use these, I think they're called tags in HTML, but it's been a long time. Let me see, HTML tags. Element? Yeah, like this, right? Thing inside. And it doesn't even need to make sense. It doesn't need to be a valid HTML thing. You can just like dash beginning and then slash beginning, right? So I don't know, just a little prompt engineering hack that I saw them doing here that I thought is interesting. Here's the 1 to 5 scale that it uses to judge. And that's pretty much it, guys. LLM mitigator mouths. I don't even know what that means. Okay. You guys have any questions? Feel free to slap them. I'm going to summarize what we reviewed today, and then I'll answer any questions. So today, the stream was called AlphaGeometry and FunSearch, but we also reviewed a couple other papers. We started off by looking at this paper here, Solving Olympiad Geometry Without Human Demonstrations. In this paper, which is a DeepMind paper, they basically solve international math Olympiad problems, which is kind of these proof problems. You can think of them like leak codes, right? Just little problems that you can solve. And the way that you solve these is basically by writing out a proof which has a specific syntactic kind of structure to it. It needs to basically be a valid set of these constructions, and then you need to eventually get to the final line of the proof, right? So basically here you start with some information here, and then you need to get to this final line here, and basically the task is to come up with a bunch of steps in between where you're basically adding all these extra pieces. And the kind of way that DeepMind is solving this is they basically are using two different parts here. One part is a language model. So they use a language model that has been pre-trained on 100 million synthetically generated proofs, right? And then fine-tuned on some subset of those. And those proofs are generated, or those proofs, which are used for the pre-training, are based around this generation process of starting from some random premise, which is the very, like kind of that first line, and then getting to the actual final thing. So basically, they use the language model to generate a bunch of next steps, and then from those next steps, you can get to more next steps, and then they create this giant graph and then trim it all the way at the end. So then they finally get to, okay, here's where the final point ended up, and then we're going to go and prune all the parts of the graph that we don't need, and then every single step in between, we can say that that step was required to get to the next step, and in that way, we've now created a synthetic proof from a random synthetic premise, and now we can just generate this data. And we do that 100 million times, fine-tune a language model on that, and then we can basically take a problem that some set of high school students was given. We feed that into our language model. The language model comes up with 10 possible little answers. We go and search down each of those 10 little answers, generate more answers, generate more answers, generate more answers, and eventually we're going to get to a point where we can say, okay, that's actually what we needed. That's the final little thing that we needed there. That's the final point, the final construction, I guess, deduction that we need, and then that's our proof, right? The problem with this paper is that the proofs that it generates are basically trash. So we saw this example in the paper where this side-by-side comparison of the human proof and the AlphaGeometry proof. The human proof is very elegant and requires this kind of out-of-the-box thinking where you go into complex numbers in what is known as coordinate bashing, right? Kind of like kit bashing, but coordinate bashing. And it's a very clean, elegant proof. The AlphaGeometry proof is this fucking tangle of 100 steps where you're just adding more shit and more shit and more shit and more shit, and eventually you get to the right answer in that, right, because this is a syntactically verifiable thing, right, these algebraic proofs, you can then say, okay, well, actually this works, or not algebraic, geometry proofs. You can say it works, but it's not actually a real proof. You know what I'm saying? It's a real proof, but it's not a real proof. It's like you just kind of brute forced it. And further evidence that points to this is this little line here on their results where they basically say that without pre-training, so just using a random language model, you can still get 21 out of 30 problems solved as opposed to 25. So that, to me, that combination of like, hey, here's an example of what a proof looks like, and hey, without pre-training, we basically get most of them anyways, means that really what they're demonstrating here is just a brute force way of solving geometry proofs, of finding geometry proofs with just brute force search. So kind of disappointing, but we only had to go a little bit further to get disappointed again with this DeepMind paper. This one's called Mathematical Discoveries from Program Search with Large Language Models. Kind of a similar idea where basically they're using a language model. The language model is generating basically programs or functions, specifically little Python functions, right? And these Python functions are evaluated by this, what they call skeleton, which is basically like a hard-coded, this is how you actually evaluate this, and then basically all we need the LLM to do is just write this heuristic function here, and we can run it, and it'll give us a score, and that score is effectively how good the solution was. So you're, again, leveraging the fact that you can use this external evaluator to make sure that the solution actually works and score the solution, and then they add this kind of like evolutionary kind of like flavor to it by basically then taking the high scoring programs and then putting them in a database and then having the high scoring programs effectively have sex with each other to create variants of the high scoring programs, right? They do that with some prompt engineering, but you basically get variants of those two, and then you run those through the LLM to generate basically the children, which have a little bit of the parents. And you just brute force the shit out of this and run it over and 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 over again, and eventually get to programs that work and that solve your problem. But much like the proof in this AlphaGeometry paper, that you just end up with these completely ununderstandable proofs that are just hundreds of steps, the same thing happens here. And the functions that you get, these Python functions that you get that quote-unquote solve this particular problem, are also very kind of brute forcey looking, right? You get look at this tangle of if-else statements, right? Like, what is this? This is not good. This is not good code, right? I'm sure the human solution to this is only a couple lines, right? And it's more intuitive. So yeah, that's kind of the same problem I have with the first DeepMind paper I have with this second DeepMind paper. And I also don't like that they try to kind of like play with words here, and they say mathematical discoveries, and they make you think that the LLM discovered some new mathematical thing. And even though it did discover a new mathematical thing, the thing that it discovered was a very high-dimensional solution. So like to this capset problem, which is this extremely niche problem that I still don't understand exactly what the fuck the point is of this problem. But yeah, I just feel like they found some extremely niche thing and then said, okay, this is the solution to a very high-dimensional variant of this already extremely niche thing. What are we even doing, right? I don't know. I feel like if it really was that good, why don't you find something that is easier to, more plebeian, more out there, like something that impresses the people. This is not impressing the people. Okay, but maybe it's just because I'm a Luddite and I don't understand math, and I'm apologies if you guys do think that the cap set is a very good and impressive problem to solve. I just don't feel like it's a very good, impressive problem to solve. Okay. Then the last two papers that we read, which I think are the more interesting papers, this is Code Generation with AlphaCodium by the folks at Codium AI. And in this one, they introduced this term called flow engineering, which is effectively what we did, or what DeepMind did in both of these papers, right? This idea of rather than just a language model generating the answer in a prompt answer kind of direct fashion, you create a flow, a kind of graph where the language model is just one node in there, and it's basically just mostly doing the generative part, which is what it's good at, and then the evaluation part of it is being done by an external system, right? In this case, rather than doing it for geometry proofs, they're doing it for general kind of coding problems. And in these coding problems, the flow that they use basically starts by first reflecting on the problem, which is just basically creating these bulleted list of like, here's more information about the problem, which the AI is doing itself, the language model is doing that itself, and then it's also generating tests. So this is basically the AI is doing test-driven development. It's creating tests, and then using those tests to improve the solutions, and then using those solutions to generate more tests, and so on. And so this kind of flywheel, this flow goes, iterates, and eventually you get to a final solution that is way better than you would have gotten to if you just basically fed this problem and asked the LLM to just generate the answer in one shot, or even 5 shots. But that's basically it. It's just generating tests is good. Generate the tests first, and then generate the answer, and then iteratively do that. Another reason I like this paper is because they give you a little free tidbits, right? They kind of have little snacks, little desserts for you to eat after you're done reading this paper. And one of the cool ones that I thought was that they basically came to the conclusion that if you're using a language model, you're better off generating YAML than JSON, which I thought was pretty cute because they say that the reason LLMs are bad at generating JSON is effectively the same reason that humans are bad at generating JSON. It's the reason people use YAML is because indentation is more intuitive, more simple, cleaner than JSON, which is the same reason people like the indentation in Python versus the kind of more explicit open bracket, close bracket, semicolon, stuff like that you see in more traditional programming languages. So I thought that was pretty cute because it basically means that a lot of the things that we have come up with as humans that make coding easier for humans are also going to make coding easier for language models, such as breaking up a problem and generating it in pieces, using bullet points, using YAML instead of JSON. Pretty cool. I thought this paper was great, and that's pretty much it. Flow engineering is kind of the keyword there, which you can use if you want to be a cool kid, but it's basically just chain of thought or tree of thought. All right, the last paper that we read was this one here called Self-Rewarding Language Models, a paper out of Meta. And in this paper, what they basically do is they use a language model as its own judge. So they take a Llama 2 70B, which is the big boy llama model, and then they use the big boy llama model to generate responses to some prompts, and then they use that same llama model to then basically rank those outputs, or reward basically a 1 to 5, how good is this? And then from that, they can create these preference pairs, which is basically for a given prompt, you have a good response and a bad response. And if you have enough of those pairs, you can create a little fine-tuning data set, and then you do this direct preference optimization, which is just the newest version of RLHF. That gives you a fine-tuned version of your Llama 2, and then you basically repeat this entire flow again, and over time, your model gets better and better and better. And not just better at generating responses, right? Improved instruction following, but it also gets better at generating rewards, reward modeling ability. So this is pretty big because it means that you don't need to have a separate reward model and a separate generative model. You can basically have a model that gets better at both of these. And I think this is a way to create basically a flywheel where a model is improving itself. And I think that type of flywheel is how you're going to get to superintelligence, right? The only instances of superintelligence that we've seen are in a game of Go, in the game of chess, things like that. And why are they in the game of Go and chess? It's because the model can generate its own data, right? You take a high-level Go AI and you make it play itself, and those games where it's playing itself are super high-level Go games, and you can fine-tune on that super high-level Go games, and then it's even better, right? So this ability to create your own data to then fine-tune and then create more data that's even higher level and higher level and higher level, that's how you get to superhuman levels, right? You're never going to get superhuman levels if what you're doing is just taking some human annotated seed data and then just RLHFing on that, or DPOing on that, right? So this ability to create a flywheel, very powerful. That's pretty much it. Like the idea for this paper is quite simple, but they do nicely kind of talk about some limitations here. I think they're honest and I like it. But basically they talk about how it's not entirely clear what reward means past a certain point, right? Where it's getting better and better at reward modeling, but reward modeling is hard to kind of quantify for a lot of kind of real world tasks, right? Where like in most real world settings, the correct answer becomes more and more nebulous when it's already pretty correct, right? And especially when you're using LLMs such as GPT-4 to judge the output, right? They're literally saying our model gets better than GPT-4 according to GPT-4. And we know that whenever you use something like GPT-4 to evaluate its output, it might be judging it based on weird things that we don't understand, such as the length of the prompt or the specific tokens that are used, or weird things that we would never care about as a human, but as an LLM, it just kind of fixates on these random things, right? So that's a potential kind of red flag here, but I think overall, this is pretty good. I think this idea of using the same model as both the actor and the critic, or the generator and the discriminator, that is very powerful, and the fact that this all works, I can't wait to see what people do with this. But that's basically it, guys. Those are the 4 papers that we read. I think, to me, I'm pretty excited because I feel like some variant of these type of things is how we're going to get artificial superintelligence, right? Some ability to, some flow like this where you can basically just plug in any LLM and then it'll get better and better and better over time. And soon we will be living in ASI utopia. So question from Ed. I can't seem to make sense of why this works. Perhaps it's easier for an LLM to determine whether the chess move is good or bad rather than attempting to make a good chess move. So in a game like chess or Go, right, you basically have the very end, you know who won the game. So when you have 2 superhuman level chess AIs playing each other, right, they play each other and then one of them wins. So then the way that reinforcement learning works is you can say, okay, well, all the moves that the one that won did going up to the final move where it actually checkmated, every single one of those moves is in some way better than all the moves that the one that lost made. It's a little bit more complicated than that, but you're basically able to say this particular chain of decisions led to a better answer, which is like the moves that you made to win the game. So it's kind of the same thing. It's like the language model is kind of choosing a bunch of tokens, right? It's picking a bunch of words in a sequence, and then ultimately one of those is going to be the winner, right? So at the very end, there's going to be one response that's the winner, YIW, and then one response that's the loser. And the response that's the winner, it's going to say, okay, well, that specific sequence of tokens, those specific words in that specific order, those were good. And those specific words in that specific order are bad, right? So it can basically compare, here's the chain of moves that got me to win the game, and here's the chain of moves that got me to lose the game, right? But the part here that's a little bit more nebulous is that in Go and chess, this reward is coming from the actual environment, like the world itself, right? Our reality is giving you that signal of like player A won, player B lost, and then you're training this usually some kind of value function, which is some other neural net, to then try to mimic and tell you what that reward is, try to guess what that reward is at any given point in the state space. But here, it's weirder because it's all in language space, so it's all text, so it's a little bit more nebulous, and also the reward model is not even a different model, it's the same model as the one that's generating. So it's a little weird, but it all works out. All right, hopefully that answers your question, Ed. If not, drop by the Discord and ask more questions. Cool, I think we're a little bit over, so I'll end it there. Thanks, everybody, for listening. Thanks, Aries, Josh, Ed, Roaming with Robert, Majetti, Liu, June, who else? Wall, Pumbaa, Spyro, Jay, Harsh, 87GN, and Tafik DP, and then Abraham Lincoln, who commented before the stream even started. Tomorrow we're going to be looking at, we're going to be doing a battle of the Mambas. So there's two different papers that got released basically on the same day, two different Mamba papers, one called V-Mamba and the other one called Vision Mamba. So I was like, dude, that's perfect. Two different Mamba papers for computer vision models on the same day, basically. It sounds like a battle to me. So we're going to be comparing those. It's probably going to get pretty nitty-gritty. So if you're interested in computer vision stuff, definitely drop by. But if you're more of an LLM person, maybe this is the one to skip. But hopefully it's useful. If not, have a great weekend. Thanks, everybody, and see you guys later.